This problem is off the 2012 AP Physics B exam. This was free response question number 4. This is another ideal gas law and really just ideal gas law, I guess. So first off, we have our gas put into a cylinder with a piston that later is going to be able to move, but right now that piston is fixed in place. And they set this at room temperature and atmospheric pressure for the inside of this chamber, this cylindrical container. So on our graph, if we're starting at room temperature and atmospheric pressure, let's just put a point here to represent that. Now, very important that this point is not at 0, 0, because room temperature is certainly not absolute 0. Atmospheric pressure is certainly not 0 in any units. So we need to show that that's not starting at 0. And then the next piece we have is that we heat this thing. It warms up because it's in a warm water bath. So if we think about the ideal gas law, PV equals nRT, we've got V held constant, and N is constant, and R is constant, so P is proportional to T. So that means that the graph of this is just going to be a straight line. But be careful. Let's make sure this straight line is aligned the way it ought to be. And that is so that if our temperature went to 0, our pressure would go to 0 as well. So you want to make sure that this is a line that it's not going to go through the origin, but it should be lined up with the origin. So something like this. And we do need to show that we have that increasing, indicate the direction of the process on the graph. Okay, next piece. This one is tricky for sure. So we take the cylinder out of the hot water bath and we let it cool off. It says after equilibrium is reached. So basically this means our cylinder is back to the same state it was at before we put it into the hot water bath. So the temperature has fallen back down, the pressure has fallen back down. And now that piston that was held in place, we're going to take the lock off of that. So now it can move around. So when we initially take that piston off, does that lock off, does our piston move up, does it move down, or does it remain stationary? Well, if we think about that piston and the forces acting on it, we have some gas inside the chamber, so that's applying a force upward that'd be equal to the pressure inside times the area of the piston. And let's see, there's air on the outside, and that'd be applying a force that would be equal to the pressure on the outside times the area of the piston. It told us in the problem that the pressure on the inside started at atmospheric pressure, so I'll just call that PA, and certainly the air on the outside is at atmospheric pressure. And so we might be tempted then to say, oh well, the piston must remain stationary here because we've got these two forces acting on it and they are balanced. But we haven't shown the whole picture. We've forgotten the force that goes on basically every free body diagram we've ever done here. So we need the mass times gravity of the piston. Now these two forces balance each other out, but this one doesn't have anything to balance it. So our piston is going to move down because the forces from the pressures, they're equal, but there's nothing opposing this pull of gravity until we move that piston down a little bit, and as it moves down, volume decreases, pressure is going to increase, so eventually we'll have more pressure inside the chamber, inside the cylindrical chamber here. We'll have more pressure in here than we do out here. Enough pressure to balance out that extra downward force from the piston, and that's when this thing is going to come to rest. All right, last one, drawing a couple of different process types on a PV diagram. So this one, first off, we let the system come back to equilibrium. So maybe when that piston fell, it would have warmed up the gas a little bit, but we're going to let it come back to equilibrium so it's back at room temperature. The pressures are going to be a little bit higher than atmospheric pressure to begin with, but we don't have any numbers shown on here, so we don't have to be real careful with that. No initial volume is given, so we're just going to pick some spot to start our graph. And then our piston is going to be pushed down very slowly. Very slowly is important here. So if the piston is pushed down very slowly, that means that we'd expect the temperature of that gas inside the piston to increase. So if we have our cylinder here and we push down our piston, that is not a good piston, there we go. Still not good, that's okay. We push this piston down, so volume is going to decrease. If we think about the ideal gas law, volume is decreasing, and if we do it quickly, it turns out that the temperature is going to increase. But here we say we do it very slowly, so that's enough time so that if we get a little higher temperature in here, we're just going to have collisions between the gases inside and the walls of the container, and that'll have collisions with the gases surrounding this. And so we have heat. We have heat being transferred out of our container, and it's being transferred at a rate to keep our temperature constant. Okay, so N and R are always constant. So for process C, what we've got is that pressure is proportional to, well, this constant. It's equal to this constant value divided by V. So it's proportional to 1 divided by the volume. Now, as I was grading your versions of these, I saw a lot of people who got to that point and then drew something like this. That is not a graph showing an inverse relationship. That's showing a direct relationship just with a negative slope. So that's not it. An inverse relationship is going to look something more like this. And I'm going to draw it a little more carefully here. We're actually starting from some point over here, and we're decreasing volume, so I know I need to the left on this scale, and then we're going to have that inverse curve, something like that. And that is process C. Then the second one says our piston is pulled up quickly, so no heat is added to or removed from the gas during the process. Okay, so now we have our piston there, and it's going to be pulled up quickly. Okay, so volume is increasing, so if you think about PV equals nRT, we've got volume increasing. What other effects do we have there? Well, let's see. If we do this quickly, that decrease in temperature that we expect when we pull the piston back, remember, because we have all these little particles inside that are moving around, and when they hit this piston, there's a little bit of give to that piston, and so they bounce off with a little less speed than they originally had, less kinetic energy. That's lower temperature. So our temperature decreases. If we did this slowly, we would just have heat flowing in from the outside. We would have heat in like this. But it tells us specifically we have no heat flowing in from the inside. So temperature is going to decrease. And so if we have both volume increase and temperature decrease, then pressure must decrease also. Now remember, pressure is decreasing here as a result of both changes in V and in T. And so as volume increases, temperature is decreasing, and so that both of these things are having an effect on the pressure. So the net effect is that pressure drops more rapidly than it would if we pulled the piston up slowly. It still would have dropped there, but not as rapidly. So now we've got pressure is equal to nR times T over V. And so pressure is proportional just to T over V. T is decreasing and V is increasing, and so P is going to be decreasing a lot. So if we come back up here, again we're going to have kind of an inverse shaped curve, but it's going to be steeper. So we start, let me stop there. Our gas ended at this point right here. So that's where we're going to start it. Whoops. Hang on. There we go. So we start it right there, and we have that curve again, but it's going to be a steeper curve. Steeper curve, something like this. And maybe it extends back to the original volume. Maybe it goes back to the same position of the piston as it was originally. That information isn't given to us. But what they were looking for in the grading guidelines here, first off, that C and D were both curves, not straight lines, but curves, and that they were concave up. So the bowl of it was bowing away from this position over here. Second thing they were looking for, or another thing they were looking for, was that the only place these two processes met was at the end of C, which was also the beginning of D. And then one more thing they were looking for was that C was drawn above D. And the last thing that they wanted to see that you understood was just the direction. So for part C, volume is decreasing and pressure is increasing, so we need to have the arrow pointing in that direction. For part D, volume increases and pressure decreases, so we need to have the arrow pointing in this direction for that one.